right, let's do a quick vocabulary slides just to make sure we are on the same page. So we're going to talk about fuzzing, which is essentially systematically testing random inputs to trigger some kind of failure on smart contracts. We'll have to define what the failure means. And there are two important concepts related with fuzzing in smart contracts. In all the systems, but particularly in smart contract, we have stateless fuzzing and stateful. And that essentially means when you're testing a smart contract, if you test in a stateless way, you only have essentially a single state, and you want to check inputs and outputs. So you don't keep track of the state at all. This is usually for libraries, for Solidity libraries, math libraries, in which you have addition, subtraction. And then there is, of course, stateful, which is most of the smart contracts nowadays. You go, you deposit, you change the state, then you withdraw, you change the state again. That's the important discussion. And some of the fuzzers that we saw over time, they only test one or the other or both. Right. The other important concept is coverage guide fuzzing. When you are generating random inputs, one good thing to have is how to distinguish between one input that you just executed from the next one. And if you cannot distinguish, you are going to do a purely random fuzzing. So you just send random inputs with the value distribution that you feel is good, and then you wait and hope to get to find a bug, right? So coverage guide fuzzing goes a bit beyond. So every time you execute, you get something back. You get like a value. You get some kind of state that you can compare. So you can say, well, I found something new, so I should keep exploring, or this is the same that I had before, so I will keep exploring. And the other thing that is important for this talk, invariant development, this is something from the last years. It's a way to develop smart contracts in which you have a list of properties that you want to enforce in your contract, and the idea is like you develop your smart contract, making sure that at each step you enforce these important system properties. You usually use fuzzers, but you can use other tools. You can use static analysis, you can use formal verification, but in this case will be for this. All right, so brief history of EVM fuzzers. More or less, this is the range that we will be covering. And then we will do some little discussions and some of the conclusions that we can get from this. Okay, so the early days, until 2018, we didn't have any fuzzing tool, all the cool stuff that we have today. The tooling ecosystem was fragmented. We had mostly static tools. You can see some of them, Securify, SmartChecks Leader, and symbolic execution tools. I put some of them, Oyente, Mitril, Manticore, Mayhem. And it was interesting that the security researchers, the people doing the tools, they didn't focus into creating fuzzing tools up to 2018. All right, and why we can see more of the symbolic execution is still around today and is useful, but at that time it was stronger because people felt more optimistic about testing the code. This is a small piece of the DAI contract that was at development at that time, and it really has a small amount of branches. It's really simple, so you can hope that symbolic execution tools can deal with that, and in fact they can. So that's why, to be fair, people were more focused into building something like symbolic execution than actually building fuzzing tools. All right, the next year, the next 2 years, we got some fuzzing tools. I developed the slides in two sides. The academia side and the industry side, and we will have some discussions about how each of them develop over time. So in the academia, we have early examples like contract fuzzer and ELF. The contract fuzzer was purely taking Geth and instrumented to do fuzzing. And ELF was a way to replace symbolic execution tools that were expensive to run, using machine learning to learn what is the type of things that we can do when we do symbolic execution in a way that is faster, right? And an interesting idea, but really didn't was not really explored further. But we can see already some trend here that the academia start with something simple and then immediately go into something more complicated. All right. In the industry side, we have fuzzers like Echidna and Harvey. Echidna is probably the first open source industrial fuzzer that we got, and Harvey follow. Harvey is closed source, and I think you can still use it on MythX. I haven't tested myself, but it's available with the consensus service. And then another example is Brownie. I like to mention because I think this is one of the first complete framework for doing developing of smart contract with fuzzing included. So it was a bit early compared to other things that we got later. All right. So the next 2 years we have more academic tools, and we have on the industry side, we have the first release of Foundry, which was which really started to change the landscape into the security tools, because Foundry got really popular or started very strong, and it featured an integrated fuzzing tool, but this integrated fuzzing tool was only for stateless fuzzing. So you can only have this kind of input-output testing. You cannot have state except that you hardcode the state inside your test, right? Typically, you put different transactions, so you can have a notion of state, but it's bundled in the actual fuzzing test. It's not a really notion of state. The other fuzzers that we mentioned, they all do stateful fuzzing. Right, but yeah, this was the first release, and it's interesting because it didn't have any coverage guide. It's just random fuzzing using one library from Rust. From the industry side, we have papers for Echidna and Harvey. Academic papers are important in the tooling landscape for the academia, because some people in academia will refuse to use your tool if you don't have a paper, even a simple one. You don't have to do very complicated work to have your paper accepted. You just have an introduction paper in which you say, this is the tool, this is what it can do. And once you have the tool, people from academia will start to look at it. Otherwise, they usually don't like it. And from the academia, we have people exploring using AFL, for the use of blockchain, in particular EVM smart contract. But this requires some heavy modifications, because AFL is very focused into execution of programs that take binary inputs and normal programs. And two more interesting examples from academia. We have Confucius, which was the first hybrid fuzzing that combines traditional fuzzing with symbolic execution, and Smartian that did simplify the actual symbolic execution to do linear constraints. So you can solve the linear constraint faster than the actual symbolic execution get better coverage. Okay, so the next 2 years we have the industry offering more tools and more refined tools. We have Foundry adding stateful fuzzing, but still mostly random inputs. And we have other tools joining: Wake, ETFuzz, and Medusa, they have releases on this period. The EDFAS is a particularly interesting one from Fastland because they also publish a paper more or less at the same time, and it's only focused on on-chain exploitation. On the other side, I like to mention the AFCF paper, which essentially takes the EVM contract and transpile it to C to later compile it, right? With that, you get much faster execution, and it's a cool idea that people definitely need to take a better look. All right, so the next year, I call it the golden year for fuzzing because if we saw the list of fuzzing campaigns, we saw a lot of people, companies doing complex fuzzing campaigns on really hard code. We have just a screenshot that I took with very well-known people in the space that did really good work. And also, Aki introduced the concept of manually guided fuzzing, in which a person annotates functions in order to define what is called flows. So every flow allows an expected or unexpected use of your smart contract. So you annotate what are preconditions, so the tool will actually explore using that as a guide. Right, it is an interesting concept. I haven't tried in deep, but yeah, definitely something for you to take a look. So the next year, tools start to reach maturity. We have Medusa reaching 1.0. We have Echidna adding some kind of symbolic execution verification using HBM infrastructure that allows to do very focused verification on some functions, on some properties. So you don't have to keep fuzzing. Once you prove this, that's it. You don't have to bother with random inputs. You can just focus the random inputs where the formal verification it's going to take too much or is not possible. And Foundry adds a proper coverage guided fuzzer with an actual corpus management, so you can save the corpus, reload the corpus. This is something that the rest of the fuzzer had, and this was based on AFL technology. It was made by an external contributor, Troy Sargent. I don't think he's here, but yeah, shout out to him for contributing to Foundry, which is such a great piece of feature. And okay, so this is the a short speed run on the latest year on how tools developed. Let's see a bit of the discussion here to see how things look like. So ecosystem still fragmented. We have tools, some people, but we have still different tools doing things in different ways and different directions. That is good and is bad at the same time. We have this, our efforts are scattered around, but it also means that we can try different ideas and see what it's working better, right? I support having multiple fuzzers just because tool has a bias. So every tool that you test will first try a certain type of inputs and then another one. So if you try different tools, you can cover more ground, right? So I support having different tools, but the ecosystem is still fragmented. Maturity takes a few years, and development is uneven. I hope with AI agents we can speed up things, but with an AI agents we cannot speed up iterating on user experience. We need the user, we need the real user to test, and then we can iterate. Almost all the tools that I mentioned don't have any kind of funding or revenue, direct revenue. The only revenue that they get is like when they do an audit or a fuzzing campaign and someone pay for that. But it's really hard to develop tools and make people pay for that. Right? At least these type of tools. And it's true that the universe of smart contract, user of a smart contract fuzzer is small. But I'm thankful of Foundry to expand this because a lot of people start to know what fuzzing is after they found that they can use it in Foundry. Okay, so the link between academia and industry, it's mostly broken. The tools that are developed for papers are later abandoned, almost immediately abandoned when the paper is out, right? Which is a shame, but also PhD students are not paid for developing and maintaining tools, and they don't have access to the actual users of the tool. So they create a tool that very few people can use or know how to use or even know of their existence, and that means that it's going to be abandoned very quickly. And it's true that the ideas sometimes are hard to see from the people working on tools from the industry. They need to look for the papers, they need to check the conferences. And the worst part is this, most of the papers are completely divorced from reality. They have artificial benchmarks that don't have any useful purpose. They have useless detectors, like they used to have, a lot of papers used to have a detector on the use of block point timestamp. That means that if your contract depends on the timestamp of the block, it's a bug. And that's not always the case. It seems like most of what they or the PhD student knows about blockchain are lottery contracts, because if you have a lottery contract and someone can control the timestamp, then you're in trouble. But otherwise, it's usually fine. And this is caused by the fact that once a paper is published with a detector like users of block timestamp, if you send another paper with a tool and it doesn't detect block timestamp usage, the reviewers will say, no, you are missing this, and therefore this is rejected, which makes no sense, right? So let's try to fix this. I know it's hard. I work in the academia, but okay. So a few slides on what worked and what was still need work to in smart contract fuzzers. In terms of auxiliary techniques, we have static analysis tools that help a lot, detecting interesting values. At the cost of slower startup, we have symbolic execution that over-promise and under-deliver, but I think we can still make it useful, especially for verify small piece of the contracts, or finding really hard values that the fuzzer will take a lot of time. And we have AI agents. Still a bit unclear how we can use it. It's clear for me that you can give Claude or Codex smart contract, complex smart contract, and they can provide a fuzzing harness. But how to actually control and direct the fuzzing campaign, this is still they still need development. Okay, so one slide to present a little bit of my own work on the future of Echidna. And I want to say that the development will continue as far as I can do it. I want Echidna to be the reference implementation. I know that the people from Recon has essentially use Echidna as a guide to write their own fuzzer for Rust, and they really do the cool job. And so I want that. I want to be a reference implementation for people who need a blockchain. Perhaps it's going to be an EVM blockchain, but perhaps it's going to be a blockchain in another blockchain. So they have a reference implementation in a high-level language like Haskell. And some upcoming features: MCP support for allowing agents to interact and direct campaigns, try to see what are the areas that has low coverage, better symbolic execution, and more aggressive corpus scheduling. All right. On the last slide, I'm going to remind that the Ethereum security quadratic funding round is still some of these tools I mentioned are participating in the quadratic funding round. So with a small donation, as little as $5, you can make a difference. So yeah. Okay, thanks for coming to the talk. I know it was an early talk, the first one on this place. So happy to take questions. Okay, Alex. So some of the features of the MCP are already on the public beta. Of course, we have simple stuff like finding coverage, like live coverage. Some hack to get live coverage. So essentially, an agent can check a fuzzing campaign in the middle instead of waiting 2 hours, 10 hours, any amount of time. It can check in the middle to say, oh, look, this part we're not reaching this part of your code. We need to do a change. We need to inject this transaction. We need to make a change. The other things that will definitely help is tracing. We can allow the actual agent to see a trace of a particular call to say, hey, we need exactly this value here in order to reach this other branch over there. All right, so these are the type of thing. And the other thing that I was also wondering is some kind of average of values. So you essentially run your fuzzing campaign, and then you get, different quantities in your contract, like the total amount of liquidity that you have. It would be cool for the agent to see which is the total amount of liquidity that was reached over the fuzzing campaign. If it's too low, then it will try to inject or will try to see why it is too low. If it's too high, it's going to adjust the values to generate better inputs. So yeah, that's more or less.